Today we are going to present to you about our final year project, which is the determination of toxicology of benzene derivative using Heteroatom Topology Index. Abstract. The use of Heteroatom Topology Index is used to calculate the molecular descriptors of benzene derivative and to analyze the dipole moment of the benzene derivative. The Heteroatom Topology Index is the degree of vertex. In this report, the first, second, and third heteroatom topology index of the certain graphs are computed. Then the bonds are determined and further linear regression analysis of the degree based on the indices with the electronegativity, bond order, and degree of vertex are carried out using the equation of first, second, and third heteroatom topology index.
In this introduction, the aim of this report is to calculate the molecular descriptors of benzene derivative and to analyze the dipole moment of benzene derivative using the heteroatom topology index. This is because the heteroatom topology index is represented in the molecular graph, which is topological or numerical value connected with the chemical constitution used in the theoretical chemistry to correlate chemical structure with various physics attribute, chemical reactivity, or biological activity. Therefore, the result will be represented as graph with the vertex representing atom and age for the covalent bond. It is also to identify properties of graph. Theoretic models can be exploited in the research of quantitative structure property relation and quantitative structure activity relationship molecules. By using heteroatom topology index, we can learn about the molecules and its properties and its use to calculate molecular descriptors of benzene derivative. For this final result, we can find the first, second, and third heteroatom topology index of certain graph are computed while the bond for the first, second, and third heteroatom topology index are determined. For further linear regression analysis of the degree-based index with the electronegative bond order and degree of vertex are carried out. During this project, the first heteroatom topology index is better than the second and third heteroatom topology index in model as it corresponding best index of the graph. In this literature review, during our research, we have known that aromatic hydrocarbon is a special class of unsaturated hydrocarbon based on a 6-carbon ring moiety called benzene. It starts where the saturated hydrocarbon cyclohexene is transformed into the aromatic hydrocarbon benzene by adding 3 alternating carbon-carbon double bonds. In nature, this arrangement of bonds rapidly alternate in the benzene structure. Because of this changing, the position of the 3 carbon-carbon double bonds make represented as a hexagon with a circle in the center and a considered less stable compound. Thus, it makes aromatic compounds are generally nonpolar and immiscible with water. As they are often unreactive, they are useful as solvent for other nonpolar compounds. Due to the high ratio of carbon to hydrogen, aromatic compounds are characterized by sooty yellow flame. Furthermore, heteroatom topology index is used to learn about the molecule and its properties. It can be used to calculate the molecular descriptors and to analyze the dipole moment of the benzene derivative, also the electronegative and bond order and its degree of vertex for each type of benzene. During this project Microsoft Excel was used to create this graph, where the regression table for benzene properties is produced by using the graph, and the link between the dependent of variable and the dependent variable is shown by R-square from the data analysis. Thus, utilizing the first, second, and third heteroatom topology index, the physical attribute of electronegative bond order and degree of vertex of benzene are represented in the study.
For methodology, after finding their chemical structures, we need to find their vertex point and then their electronegativity, bond order, and degree. After that, we can find their HTI1, HTI2, and HTI3.
So I'm going to show you how we find our HTI1. We start the formula with equal, open bracket, select the first electronegativity on the first vertex, powered by 2, plus the second electronegativity, powered by 2, close the bracket. The power rate here, we change it to power of 0.5, and then divide it to the first degree on the first vertex point, and then close the bracket. That's the formula on how to find the HTI1, and then continue with the second vertex, third vertex, fourth, fifth. The second vertex will be plus with 1. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 plus with 1, 3 plus with 2, 4 plus with 3, and then continue until the 6th vertex. For the 7th vertex, we plus it with 1 because 7 vertex connected with the first vertex. Okay, so 7 plus 1, 7 power by 2 plus 1 power of 2, and then power of 0.5 again, and then divided by the 7 degree, and continue to the 8, 9, 10, 11, and 12. So at the end, we will get the result, which is 7.7200138822. For HDI2, the formula will be start with the bracket and then put 11 star, bracket again, then select the first electronegativity powered by 2 plus the second electronegativity powered by 2, close the bracket, and power of 0.5 because they also have the power root here, and then close the bracket, and then just continue with the second vertex. The second vertex will be 12 star, open bracket, second electronegativity powered by 2 plus third vertex powered by 2 again, and then powered by 0.5, and then close the bracket. If you can see here, this is 11 for the first vertex, 12 for the second vertex, and it will continue here. This is 11, this is 12, this is 13, 14, 15, 16, 17, 18, 19. However, this one will be 110, not 20. 110, and then continue with 111, and then continue with 112. If you have 13 vertex point, then it will be 113, and then continue like that. So at the end, when you finish the formula until the 12th vertex, you will get 703,554, 1849. For HDI3, the formula will be equal 1 over, open bracket, the first degree point, minus 11, close the bracket, powered by 2, and just continue the formula with the second vertex, third vertex, and so on. Okay, plus 1 over the second degree, minus 12, powered by 2, plus 1 over the third degree, minus by 13, close, powered by 2, until the end. For the 10 vertex, we will use 110, just like the second HDI. And then at the end of the formula, after complete all the formula, you'll get 0.07389,773.
For results and analysis, we obtain HDI1, HDI2, and HDI3 for each of the 90 molecules. The calculation of HDI for each molecule is based on the chemical structure of the molecules. Dipole moment has been provided to us. 90 benzene are examined to gain insight into their physical properties. This toxicology of benzene levels is calculated using a computer program called Microsoft Excel. For the graph for both reports, we use regression analysis and enter the dipole moment data at input Y and the HDI1, HDI2, and HDI3 data at input X. So, this is the summary output that we have obtained for report 1 and report 2. This is the line fit plot of HDI1, HDI2, and HDI3 in report 1 that we have obtained. While this line fit plot is in report 2, this graph plots dipole moment against HDI, where dipole moment is the y-axis and HDI is the x-axis. Then, the residue plot of HDI1, HDI2, and HDI3 in report 1. The sum of squares for the residue in this report 1 is 6.7070. And next, the residue plot of HDI in report 2. The sum of squares for the residue in this report 2 is 88.0563. This graph plots residue against HDI, where residence is the y-axis and HDI is the x-axis.
For our report, it will divide by 2. So, for discussion 1, topological indices display each chemical structure's numerical value while remaining as unbiased as possible. The chemical structures may be classified using these indices, and chemical and biology properties can be predicted using them. 90 benzene are examined based on table 1 to gain insight into their physical properties. This toxicology of benzene levels are calculated using a computer program called Microsoft Excel. Table 1 shows the values of the first, second, and third heteroatom topology indexes as well as the charge point and dipole moment. The physical properties of benzene that must be determined are the heteroatom topology index. On the foundation of the regression we created in Microsoft Excel, a total of 6 graphs were generated. Line fit plot and residual plot graphs are the graphs we get from the software. This graph depicts the relationship between the theoretical and calculated dipole moment values. The R2 value that we obtained was 0.0952, and the linear equation is y equal to negative 0.897 plus HDI1 plus 0.0118, HDI2 plus 26.0773 HDI3. The mechanisms of benzene toxicity has been linked to reactive metabolites like benzene oxide. Acute exposure can cause sleepiness, disorientation, delirium, loss of consciousness, respiratory arrest, and death, which are all symptoms of solvent intoxication. That's why we must be very careful when we do research and study about benzene. Next, for discussion 2, topological indices display each chemical structure's numerical value while remaining as unbiased as possible. The chemical structures may be classified using these indices, and chemical and biological properties can be predicted using them. 90 benzene are examined based on Table 2 to gain insight into their physical properties. These toxicological of benzene levels are calculated using a computer program called Microsoft Excel. Table 2 shows the value of the first, second, and third heteroatom topological indices, as well as the charge points and dipole moment. The main objectives of this research are to calculate the molecular descriptors of benzene derivative using heteroatom topology index, and to analyze the toxicity benzene derivative using heteroatom topology index, also to analyze dipole moment of the benzene derivative using heteroatom topology index. Therefore, by using heteroatom topology index, we can find the R-square of this table is 0.9196, which is present for the calculation of atom and bond parameters for heteroatom containing molecules used in computing graph theoretic invariance. In the first approach, the atom and bond weight are computed on the basis of relative atomic electronegativity using carbon as standard. In the second system, the relative covalent radii are used to compute atom and bond weight, again with the carbon atom as standard. Thus, from here we can find the equation that occur during heteroatom topology index, which LD50 equal to 0.1376 HDI1 minus 0.0101 HDI2 plus 70.4836 HDI3, and find dipole moment that happen for overall each component is 70.620302. The new definition of the atom and bond parameters leads to a periodic variation versus the atomic number Z, with a more natural variation when compared with the parameters defined only by Z. The two approaches are used to define and compute topological indices based on graph distance. A quantitative structure property relationship study is reported for boiling points of 185 acyclic compounds with 1 or 2 oxygen or sulfur atoms, in terms of 4 or 5 molecular descriptors. Benzene is hardly pointed as the component with most toxicity, as benzene evaporates into the air very quickly. Its vapor is heavier than air and may sink into low-lying areas. When inhaled or swallowed, benzene has been found to cause different types of tumors in lab animals such as rats and mice. These results support the finding of an excess risk of leukemia in humans, as it can cause chromosome changes in bone marrow cells in the bone marrow when new blood cells are made. Such changes are commonly found in human leukemia cells. Benzene causes harmful effects on the bone marrow and can cause a decrease in red blood cells, leading to anemia. It can also cause excessive bleeding and can affect the immune system, increasing the change for infection.
In conclusion, the topological index is usually used to determine the physical properties of a chemical compound. Benzene is known as a special class of unsaturated hydrocarbon based on a six-carbon ring molecule called aromatic hydrocarbon. The chemical formula of the aromatic hydrocarbon is CCHC. When the branch of aromatic hydrocarbon become longer, its physical properties are changed. When the hydrogen atom is removed, the alkene structure calculated between the vertices of carbon at the edge of the compound. The electronegativity, bond order, and degree of vertex benzene can be examined by using graph theory. In this slide, we list all the references that we use to finish our final year project.